introduction for this project, interpolation is a mathematical technique used to estimate unknown values between known data points. It is widely used in engineering, science, data analysis, and also computer application. Different interpolation methods may produce different approximation and curve behaviors. Lastly, this project develops a MATLAB application to compare multiple interpolation methods visually.
So now I will continue with the objective. So the main objective of this project is to develop an interactive MATLAB application for interpolation analysis. This application allows users to perform interpolation using 3 different methods, namely Lagrange interpolation, Newton divided difference, and cubic spline interpolation. Besides calculating interpolated values, the application also visualizes the result through graph, making it easier for users to understand the behavior of each method. Lastly, the app enables users to compare different interpolation methods and observe their difference in terms of approximation and smoothness. Our application implements 3 interpolation methods. The first method is Lagrange interpolation. It constructs a polynomial that passes through all given data points and is suitable for interpolation problems involving a small number of points. The second method is Newton divided difference. This method uses a divided difference coefficients and provides a more efficient way to update the interpolation polynomial when new data points are added. The third method is cubic spline interpolation. Unlike the previous methods that generates a single polynomial, cubic spline creates a series of piecewise cubic functions, resulting in a smoother curve between data points. These 3 methods were selected because they allow users to compare different interpolation approaches and observe their difference visually.
The code starts by reading the user input, including the x value, y values, interpolation point, and interpolation method. Next, the program validates the input data to ensure that the values entered are correct, and the selected interpolation algorithm is then executed to calculate the interpolated value. Finally, the result is displayed and a graph is generated to visualize the original data points, interpolation curve, and also interpolated point. This application allows users to enter data points, select an interpolation method, and specify an interpolation point. The application then calculates the result automatically and displays both the graph and interpolated value.
Now, I will demonstrate our interpolation application using Lagrange method. First, enter the fixed data. For x value is 1, 2, 3, 4, and 5, and for y value 1, 5, 2, 8, and 3. Next, enter 2.5 as the interpolation value. This means that the system will estimate the y value when x equal to 2.5. Then, select Lagrange from the drop-down menu. In the code, when I click Calculate, the application reads the input data, checks whether the inputs are valid, and runs the Lagrange interpolation calculations. Now, click Calculate. The application gives the result, which is approximately 2.5312. Next, from the graph, the blue circle shows the original data point. The red curve shows the interpolation curve generated using the Lagrange method. And the black square shows the estimate value at x, which is 2.5. From the graph, we can clearly see how the interpolation predicts value between existing data points.
As explained by the previous presenter, the Lagrange interpolation method uses a single polynomial that passes through all the given data points. Newton interpolation is quite similar to Lagrange because both methods produce the same interpolation polynomial and therefore give the same interpolated value for a given dataset. However, Newton interpolation is computationally more efficient because it uses divided difference. If a new data point is added, only the additional terms need to be calculated, whereas Lagrange interpolation usually requires the entire polynomial to be reconstructed. The blue circle represents the original data points, while the red curve represents the interpolation polynomial generated using the Newton method. The black square shows the estimated value at x equal to 2.5. Which is approximately 2.5312. Since Newton and Lagrange generate the same interpolation polynomial, the graph obtained here is almost identical to the graph shown in the previous Lagrange demonstration. Next, we go to the cubic spline demonstration. Unlike Newton and Lagrange interpolation, qubit spline does not use a single polynomial across the entire interval. Instead, qubit spline constructs several qubit polynomials between consecutive data points and joins them smoothly together. As we can see from the qubit spline graph, the curve is generally smoother than the Newton interpolation curve. This smoothness occurs because the first and second derivatives are continuous at every joining point, creating a natural-looking curve.
Next, I will explain the main features of our application. The application has a user-friendly GUI and supports three interpolation methods, which is Lagrange, Newton, and spline interpolation. It also provides graph visualization, allows easy comparison between methods, and performs calculations automatically. In addition, the input and output data are displayed clearly for users. Overall, this application helps users understand interpolation techniques more effectively. In conclusion, this project successfully developed an interactive interpolation application that combines numerical computation with graphical visualization. By implementing Lagrange, Newton, and spline interpolation methods, the application allows users to calculate, visualize, and compare interpolation results easily.